You must have come across the term buffer solutions, particularly while discussing about or reading about certain reactions. Now, in this video, we shall go through what buffer solutions are, what are its characteristic features, applications, etc., etc. Buffer solutions are those solutions whose pH does not change even on addition of small amount of acid or base, or rather we can say it resists any change in pH when some amount of acid or base is added to it. Now we have got two types of buffer solutions basically, that is acidic buffer and basic buffer. Now, acidic buffer is a buffer solution which has a pH less than 7. It is commonly made from a combination of weak acid and its strong salt, like a weak acid and a strong salt of the same acid. For example, a solution of acetic acid and sodium acetate. So acetic acid is a weak acid, sodium acetate is a strong salt of it. It is made from weak acid and a strong base, sodium acetic acid and sodium hydroxide. Now, we can have different types, different acidic buffers by having a combination of any weak acid and a strong salt of it, the same. Now, basic buffer are those buffer solutions which has a pH greater than 7. Now, basic buffer solutions are made from weak base and a strong salt of the same. For example, a combination or a mixture of ammonium hydroxide and ammonium chloride forms a basic buffer. Now, the characteristic features of any buffer solution, be it acidic or basic, number one is that it has a definite pH value, and then its pH remains unaltered with time. Even you can prepare this buffer solution and keep its pH will not change on time. And then the pH remains unaltered even on addition of small amount of acid or base to it. These are the three main characteristic features of buffer solutions. Now let us see how the buffer solutions resist the change in pH. That is the mechanism of buffer action. Let us take the example of, or let us take the case of acidic buffer. Now, an example for acidic buffer is a mixture of acetic acid and sodium acetate. Now, when you consider this mixture, the mixture will be having acetate ion and sodium ions from sodium acetate, and since sodium acetate is a strong electrolyte or a strong salt, it will ionize completely. And acetic acid also will ionize to form acetate ion and H plus ion. But since acetic acid is a weak acid, it will ionize incompletely, or only partial ionization of acetic acid happens. Now, so you can say that in the solution, in the acidic buffer solution, you will be having acetate ions, sodium ions, H plus ions and acetic acid. Alright, now when you add some amount of acid to this buffer solution, now acid will react with either a base or a negatively charged ion. So here in this mixture, what we have is, we don't have a base as such, but we have a negatively charged ion, the acetate ion. So when we add acid, what happens? It will combine with acetate ion to form its acetic acid. Now remember, acetic acid is a weak acid, so it will not ionize. Alright, so on adding acid, the acetate ions are trapped. So the pH of the solution, or you can say on adding acid, the H plus ion of the added acid is trapped by the acetate ion, and hence the pH of the solution will not change. Now when we add a base to this, what happens? Now when we add a base usually reacts either with a positively charged ion or an acid. Now, so the possible species which can combine or react with the base are Na+, H+, or acetic acid. Now when you add a base, that is an OH minus, if it combines with sodium, it forms sodium hydroxide. So that will again, it's a strong base, so it will ionize, so that is not going to happen. What happens when you add a base is it will combine with the acetic acid and form acetate ion and water. So the added OH minus combines with acetate ion. So the pH again is not going to change. So this is how an acidic buffer acts, or an acidic buffer resists the change in pH. Now let us see how a basic buffer will resist the change in pH. As an example, we shall take ammonium hydroxide and ammonium chloride mixture. Ammonium chloride will completely dissociate to form ammonium ion and chloride ion. It's a strong salt. And ammonium hydroxide will incomplete or partially dissociate to, it must be the other way around. Ammonium hydroxide will dissociate to ammonium ion and hydroxide ion. Now when we add an acid to this combination, so if in this mixture, in the basic buffer mixture, we'll have ammonium ions, chloride ions, ammonium hydroxide and hydroxide ions, some amount of hydroxide ions. Now when we add acid can combine either with ammonium hydroxide or with chloride ion or with OH minus. And when we add acid, the acid will combine with ammonium hydroxide to form ammonium ion and H2O. So ammonium ions are formed, or you can say the acid, the H+ ion is trapped by ammonium hydroxide. Thus the pH is not changed. And when we add a base to this, the base can combine with either ammonium ions, that is the only possibility, ammonium ion. The base can combine with ammonium ion. So ammonium ion and OH minus ion will combine to form ammonium hydroxide, and we know that ammonium hydroxide is a weak base. It will not dissociate, so OH minus ion is trapped. And thus the pH of the solution will not change, or pH of the buffer will not change. So this is the way how a basic buffer will resist the change in its pH. Now, let us see how the buffer, a salt, that is a salt of a weak acid and a weak base also forms a buffer. Okay, salt solution of a weak acid and a weak base, like ammonium acetate. Acetic acid and ammonium hydroxide combine to form ammonium acetate. Both acetic acid and ammonium hydroxide are weak base, with a weak acid and weak base. So you take this buffer, it will have, the solution will be having acetate ions and ammonium ions. When you add an acid to this, the acid will combine with acetate ion to form acetic acid. Since acetic acid is a weak acid, it is not going to ionize, and hence the added H+ is trapped. So the pH of the solution will not change. When we add a base, what happens? The base will combine with the ammonium ion and form ammonium hydroxide. So you get a weak base. So again, the pH is not going to be altered. So the added base and acid is trapped by the ions present in the buffer. So in any case, be it acidic buffer, basic buffer, or a buffer of salt of weak acid and weak base, the added acid and base is trapped by the ions present in the buffer. And these ions combine with the added acid and base and forms a weak electrolyte. Thus, the pH of the solution is not altered. Now, along with this, we need to know something, one more concept, that is the buffer index beta. Now, buffer index beta is nothing but a ratio of the increment of the added strong acid or base to the variation in pH. That is the ratio of how much acid or base is added and what is the change in pH, that ratio. So, beta is equal to dB by dpH, where dB is the small change in the strong acid or base and dpH is the small variation in the pH on adding this acid or base. There will be a slight variation. Okay, that is what is said, but not very pronounced. A slight variation is expected. And that variation is quantified as buffer index. Now, the dB, that is the small increment in the acid or base added to the buffer solution, is expressed in terms of moles per kg. And it is considered that beta, that is this ratio, is always taken as positive value. It takes up positive value. When a strong base is added, both dB and pH are positive because when you add a base, pH increases, isn't it? So the change in pH also will be positive. So the buffer index will be positive. Now when you add a strong acid, the change in pH will be negative because pH decreases. And hence dB will also be negative. Then only beta will be positive. Alright, so on adding base, dB and dpH will be positive. On adding an acid, dB and dpH will be negative. This is in order to maintain positive value for beta or buffer index. So these are the basic informations which we need to know about buffer solution and buffer characteristics of buffer solution. Now, what are the applications of buffer solution? One very important application of buffer solution is in analytical chemistry. That is, during our salt analysis, quantitative and both in quantitative and qualitative analysis, we need to maintain constant pH. So, for certain reactions particularly, so we add buffer solutions to maintain constant pH. Say for example, for the elimination of phosphate ion in qualitative analysis, acetic acid sodium acetate buffer is added. And in complexometric titration of EDTA, ammonium hydroxide, ammonium chloride, a basic buffer is added. So when you add a buffer, the pH of the solution will not change. We need to maintain a constant pH, then only we get good result. So that's application of buffer solution in analytical chemistry. Then for tanning of leather and fermentation, the pH is to be maintained, so we add buffer solution. Then for calibrating various equipments, particularly pH meters, we need buffer solution so that constant pH is maintained. So for the calibration of sensitive equipment like pH meters, we need buffer solution. And most of the biological reactions happen at a constant pH, particularly the enzymatic reactions. So our body has got its own mechanism to maintain constant pH or to have a buffer effect in our body, so that the all our reactions, the biological reactions happens correctly and efficiently. So these are the applications of buffer solution. Now let us see how can we quantify the pH of buffer solutions, or how can we calculate the pH of a buffer solution. Now this is being given by, that is the pH of a buffer solution, the expression for pH of a buffer solution is given by Henderson's equation. It is also known as Henderson's Hasselbalch equation. Certain texts refer it to as Henderson's Hasselbalch equation. Now, Henderson's equation is useful for estimating the pH of a buffer solution and also to find the pH in an acid-base reaction. And its general formula for Henderson equation is pH equal to pKa plus log salt by acid or base. In the case of, if it is acid, it will be pH equal to pKa plus log salt by acid, or if it is for base, pH equal to pKb plus log concentration of salt divided by concentration of base. Now, this equation can be used to determine the amount of acid or base required to make a buffer solution of a particular pH, or it can be used to determine the pH of a solution when a particular concentration of salt and acid is used. Now let us see how do we arrive at this expression. Let us take the case of an acidic buffer. An acidic buffer will be a combination of HA and weak acid and a strong salt. And the weak acid will undergo incomplete dissociation and the strong salt will undergo complete dissociation. So in the acidic buffer we will be having ions H plus, A minus, B plus and A minus, and most of the A minus will be coming from the salt Ba. Now keeping this in mind, let's move forward. Let us try the ionization constant Ka for the acid. The ionization constant expression will be Ka equal to concentration of H plus into concentration of A minus divided by concentration of Ha. Now we can rearrange this and take H plus, concentration of H plus to the left hand side. We get the expression like this. Concentration of H plus equal to Ka into concentration of Ha by A minus, concentration of A minus. Now, taking log or another thing before that, we can, as I said earlier, most of the A minus comes from the dissociation of the strong salt Ba, so we can equate concentration of A minus to the concentration of Ba. So you can rewrite this equation as concentration of H plus equal to Ka into concentration of acid by salt, or concentration of Ha by concentration of Ba. Now taking log on both sides and giving it, making it negative. Taking log, we get log H plus equal to log Ka plus log concentration of acid by salt. Taking negative, making it negative, we get negative log concentration of H plus equal to minus log Ka plus log Ba by Ha. We have taken the reciprocal of this term. Now we know that negative log H plus is nothing but pH and negative log Ka will be pKa. So we can rewrite this equation as pH equal to pKa plus log concentration of salt by concentration of acid. So this is the Henderson-Hasselbalch equation or Henderson's equation for acidic buffer. Now using this equation, if the concentration of salt and acid is known, we can calculate the pH of the solution. If we want to if we want to prepare a solution or buffer solution of a particular pH, we can, using this Henderson equation, we can determine what must be the concentration of salt and acid which is to be used. So these are the applications and the utility of Henderson's equation. Now, for the case of basic buffer, it's similar, the derivation is similar. The only major difference is that instead of acid, we'll be taking here a weak base, BOH. Now, since the base is weak, it will undergo incomplete dissociation, and since the salt is strong, it will undergo complete dissociation. And taking the ionization constant of the base, we get Kb equal to concentration of B plus into concentration of OH minus divided by concentration of BOH from the equation of incomplete dissociation of BOH. Now you rearrange this equation, take OH, concentration of OH minus to left hand side, we get the expression in this form. Concentration of OH minus equal to Kb into concentration of BOH divided by concentration of B plus. And again, the way we have assumed in acidic buffer here also, we know that most of the B plus ions come from the complete dissociation of Ba rather than from the dissociation of the base. So we can equate the concentration of B plus to the concentration of BA, and hence we can rewrite the expression as concentration of OH minus equal to Kb into concentration of BOH divided by concentration of BA. Taking negative logarithm on both sides and making it negative, what we get is minus log OH minus equal to minus log Kb plus log concentration of BA by concentration of BOH. We know minus log OH minus is nothing but BOH, and minus log Kb will be pKb. So we get POH equal to pKb plus log concentration of salt by concentration of base. This is the Henderson equation, or Henderson's Hasselbalch equation for basic buffer, POH of a basic buffer. Now, if you want to get the pH of this basic buffer, what we can do is, we know that pH is equal to 14 minus POH. Using this term, we can calculate the pH of the basic buffer. So if we know the concentration of salt and base used, we can calculate the POH, and through that we can calculate the pH of the basic buffer. Or if we know the pH of the basic buffer, automatically we can measure, or we can calculate how much amount of salt or base is required. Now, using these two equations, we can prepare buffer solutions of our required pH. Now, this is the Henderson's equation, and I have explained what buffer solutions are, etc. Its applications and all. Hope it's clear. Try to solve problems related to the Henderson's equation. Thank you.